Hello students, today we are going to solve a specific exercise, and that is there are two continuously steered tank reactors, CSTRs, which are similar in many aspects, and we have to compare the heat transfer coefficients between them. And the task is to convert or compare the Nusselt number in relation to the heat transfer with other dimensionless numbers. And of course, the moment we hear dimensionless numbers, we know that we have to carry out a dimensional analysis. And that is exactly what we are going to do in this exercise. We are going to do a dimensional analysis to see what are the different parameters that H depends on. So H is the heat transfer coefficient, and what does it really depend on? It does depend on the conductivity of your fluid, so that's lambda. And then it's a fluid flow, right? So as you have already seen in the analysis of drag forces, there are certain parameters that we can easily associate to such a flow. For example, the characteristic diameter of the system, d. And then the velocity of the system, v. You also have the fluid properties, such as the density as well as the viscosity, mu, of the fluid. The only extra parameter that you need here is the specific heat, because we are talking about a certain mass of the entire fluid volume. Please note that in this case, it is mentioned in the exercise that the velocity v is in terms of a steering speed of your steerer, that's n. Now we're going to write the overall heat transfer coefficient h as a function of all these parameters. So first, h, let's put a dimensionless constant k, which takes care of all the constants in the relationship. And then the first parameter that we have is conductivity lambda raised to the power a, then the diameter d raised to the power b, and then we have the steering speed, that is n, that is raised to the power c. We have density rho of fluid raised to the power d, and the viscosity mu of the fluid raised to the power e, as well as the final one, specific heat C sub p raised to the power f. That's the entire functional relationship where a, b, c, d, e, and f are unknowns. And that's what we would like to find out. How does small h, the overall heat transfer coefficient, depend on all these parameters exactly? So as you already know from dimensional analysis, we have to write down the dimensions, the units, especially in this case, the SI units of these parameters. So let's start with overall heat transfer coefficient. As you know, overall heat transfer coefficient is joules times joules divided by second meter squared times Kelvin. We are going to break down the joules here. Joules is the unit of energy, so we are going to break it down into force times displacement, and force in turn from Newton's second law is mass times acceleration. So mass kilograms times acceleration is meters divided by second squared, then that is just the force times a displacement, that gives you the total energy, so that's joules, and then you still have the rest in your expression. So this is the entire expression. As you can see, the meter squared, that cancels out both from numerator and denominator, and we are left with kilograms divided by second cubed times Kelvin. That is the SI unit of heat transfer coefficient. So we are going to write that down on the left hand side of our equation. Kilograms second cube Kelvin. On the right hand side, it's easier. For dimensionless constant K, you do not have any dimension, any unit. So that's easy. And then we are going to go to the next ones. For conductivity, it is kilograms meter per second cube Kelvin to the power A. For capital D, diameter or characteristic dimension of the system, it's of course a length, so just meters to the raised to the power B. The third term here is the steering speed that's given in your exercise to be just inverse of second. So that raised to the power C. Density rho is always kilograms per meter cubed in SI units to the power D. Finally, you have the viscosity, which is kilograms meter second to the power E, and the specific heat Cp is meter squared S squared K all raised to the power F, small f. So now we've written down all the dimensions of left hand side variables as well as the right hand side parameters, and our task is then to equate all this. So we start with kilograms. On left hand side, you only have 1 kilogram. On the right hand side, I see there is A from here, then nothing, nothing, and then here again you have D, and finally from viscosity, so raised to the power E. So we are now matching just the powers. Let's call this equation equation 1. The second one is for length, meter. On the left hand side, there is no length, so it's just 0. On the right hand side, you have A plus 1 from here, 1 from B, so A plus B. Then you have here minus 3 times D, so minus 3D. And finally, you also have 1 from E, minus E because it's on the denominator, and also here plus 2F in the specific heat. Let's call this equation number 2. After meter, we are going to go to the unit of time, seconds. On the left hand side, I have minus 3 here, minus 3. Right hand side here is minus 3a from the first term, then nothing, then I have minus c from the velocity term, then nothing from the density term, but there is 1 minus e from the viscosity term, and finally we have minus 2f from the specific heat term. I think yes. So let's call this equation number 3, and the final term that we have is of course the unit of temperature, so that's Kelvin, and we can write that as here only minus 1, and that is equal to here 1 minus a, and another one is here minus f. Together we form the equation number 4. As you can see, we have 4 equations, but we already defined 6 unknowns here, a, small a, all the way to small f. So that's 6 unknowns. So we will never be able to solve this completely, this set of equations. But what we can do is express these unknown parameters in terms of one other unknown parameter. Let's say we can choose 2 out of this, and we express the rest 4 in terms of those 2 parameters. That is possible from these 4 equations, and then we have a functional relationship. If you do that, then you find out that A turns out to be 1 minus f, B turns out to be 2d minus 1, C is just d. We have chosen in this particular variation to express everything in terms of d and f, so we are not going to write any expression for d. E is the same as f minus d. And finally, again, for f, we do not write any expression because we expressed everything in terms of either in terms of d or in terms of f. If we write this down back here in our original expression of h, then it turns out to be something like this. K lambda times 1 minus f d capital D to the power 2 small d minus 1, then the steering speed raised to the power d, the density of fluid raised to the power d, the viscosity mu raised to the power f minus d, and finally the specific heat, which is just f. Once we have written down the expression for overall transfer coefficient, heat transfer coefficient h in this form, it's a matter of rearranging all those parameters. So let's try that. We can write then h equals, this k remains, so let's just write k, and then this coefficients 1 and here minus 1, we are going to write them together. So that is a lambda divided by capital D, the characteristic dimension of your system. The rest we are going to rearrange in a different way. We are going to write all the equations either in term of d or in term of f. If you do that, then it turns out to be rho times f n d square divided by the viscosity raised to the power d, whereas left hand the other remaining term will then be mu times Cp, mu of f times Cp divided by lambda raised to the power f. So let's bring this independent term of conductivity divided by the characteristic dimension on the left hand side. This ratio looks familiar to you because this is the definition of Nusselt number, the convective heat transfer divided by the conductive heat transfer. On the right hand side, this term is again familiar to you, the density times the in this case the rotation number of your steerer times the diameter of characteristic dimension of your system squared. This is nothing but the density times the velocity times the characteristic dimension, and then in the denominator you already have the viscosity, so this is the Reynolds number. And as you also know, then the viscous momentum transfer divided by the conductive diffusivity is your Prandtl number. So that is indeed the other dimensionless number that we are looking for, which is the Prandtl number. We are going to write this as the Nusselt number, which is then a function of Reynolds number and Prandtl number. And that is the final expression, that Nusselt number is actually dependent on the Reynolds number and the Prandtl number. The fact that Nusselt number is dependent on Prandtl number is no surprise, because of course you need a heat transfer element in your equation. But at the same time, we find out that Nusselt number is also dependent on Reynolds number. So that is the essence of convective heat transfer, where you need a flow element to come into your equation. And that flow element comes from the Reynolds number, of course, which is the ratio of inertial forces divided by the viscous forces.